Here we have section 3.4. I think this is a pretty fun section. So we're talking about concavity today. So you can read through that first paragraph, but we're going to jump right to example 1. So let f of x be a function such that f prime of x is positive on some interval. So it means the function needs to be increasing. So 3 ways that we could have increasing would be maybe something like that, or it could be increasing this way, or maybe it's increasing at a more constant rate. So if you look at the slopes for each of these, in example 1, the slopes are increasing. It's getting steeper as the x values increase. In this one, the slopes are decreasing. It's getting less steep. And in number 3, the slopes are constant. So these are all increasing over the interval, but they're curving differently. And this is where concavity talks in. Okay, so if f prime, if the slope tells us how the y values of f are changing, then the second derivative tells us how the slopes are changing. All right, so here's a good easy way to remember it. Concave up like a cup. If it looks like this, it's concave up. Concave down like a frown. Okay, or zero concavity curve depravity. If it's really flat and boring there, if the slopes aren't changing, the slopes are constant, then there is no concavity. All right, so for each of these, we're going to determine the signs of f prime and f double prime. So I'm going to just focus on f prime for right now. That's talking about whether f is increasing or decreasing. So f increases here, f decreases, whoops, f is decreasing. Come on. And f is increasing. Now let's look at f double prime. The top 2 are concave down like a frown. And the bottom 2 are concave up like a cup. All right, so this gives you a nice little chart just to look at each of these to determine increasing and concavity. All right, so now just as relative extreme values occur at critical values, that's where the slope changes from positive to negative or negative to positive, we can have inflection values where the second derivative changes signs. Okay, so for example, there's an inflection value at x equals p here because the graph goes from concave down to concave up. There's an inflection value here because the graph goes from concave up like a cup to concave down like a frown. Okay, this one, there is no inflection value at x equals p, even though the graph changes how it looks a little bit, because it is concave up like a cup and also concave up like a cup. This changes from concave down like a frown to concave up like a cup, but there is no inflection value there because it's discontinuous. So even though a graph can change concavity at a discontinuity, it will not be an inflection value at that point. Oh, let's change the page. There we go. Oh, it changed twice. There we go. A possible inflection value, or we'll just call it PIV, is an x value in the domain, that's important, such that the second derivative is 0 or undefined. All right, so if we look at this function, we're looking for possible inflection values. Where does the concavity possibly change? All right, so that would be at B, C. It goes from concave up like a cup to concave down like a frown. You know what, this is going to help us to make a little chart here, and it's going to help us for the next section. So we have x, we have f double prime. We're talking about concavity now. So we have v, c, d, e, h. Well, let's see. I'm not going to include the endpoints because that doesn't make sense. All right. So now I know I only listed B and C. Let me organize this a little better. So it looks like it's concave down like a frown, then it's concave up like a cup, down like a frown. Between D and E, it's up like a cup, and between E and H, it's up like a cup, and on the other side of H, it's down like a frown. So when I list possible inflection values, that could occur at B, C, D, E, or H. Now determine if f of x has an inflection value. It has an inflection value at B, C, and D, since f double prime changes signs there. Okay, note the graph doesn't change, the second derivative doesn't change signs at E, and although the signs change at H is not, there's a discontinuity there, so we can't have an inflection point if it's a discontinuity. So now we're going to list the open intervals. F is concave up. F is concave up like a cup on the intervals from B to C. We're looking for the positive values, D to E, and also from E to H. Okay, F is concave down like a frown on A to B, also from C to D, and also from H to K. So there you go. All right, so I just kind of introduced you to that second derivative number line chart. So we're focusing on finding inflection values and open intervals of concavity. Remember, not every possible inflection value is an inflection value. The concavity must change, and it can't be a discontinuity in order to be an inflection point. All right, so we're going to do a couple of these examples, but I don't want to do all of these in the video. Just for the sake of time, I think you could get a lot of practice with it yourself, and you'll get a lot of practice in the worksheet. All right, so let's focus. We got to find the second derivative if we're finding the possible inflection values. So let's start with the first derivative here. Y prime would be cosine of x. Y double prime would then be negative sine of x. Okay, so where is negative sine of x equal to 0? And that would be on our interval here, x equals 0, pi, and 2 pi. So we're going to put those on our number line, or our sign chart. And we're checking the signs of y double prime. Now, since 0 and 2 pi are our endpoints, I'm just going to check the values in between them. And if I check pi over 2, that looks like that would be positive, and 3 pi over 2 would be negative. So to answer this question, find the possible inflection values. There would be possible inflection values would be at x equals pi, because the second, oops, why am I doing pi over something? X equals pi. The inflection values with justification, so x equals pi is an inflection point, or an inflection value, since y double prime changes signs. And then the last thing we need open intervals of concavity. So y is concave up like a cup from 0 to pi, and it's concave down like a frown from pi to 2 pi. All right, so we did this one already. Okay, I'm going to clear this out. I think I am. Let's try it this way. Okay, like I said, we're not going to do all of these together, so we did this one already. Let's do letter C. All right, so g prime of x, the first derivative. Let me note also that x cannot equal negative or positive 2. Uh, okay, so just for the sake of time, I did this on a scrap paper. If you don't trust me, do it yourself and tell me I did something wrong. So negative 10x over x squared minus 4 quantity squared. And then if you take the second derivative, you should end up with 10 times the quantity 3x squared plus 4 over x squared minus 4 to the third. All right, so possible inflection values occur at oops, I'm writing I and A. Part 1, that would be x equals plus or minus 2. Part 2, because the numerator won't equal 0. It's always positive. If we draw our graph here, negative 2, 2, we're checking the sign of G double prime. Looks like it is positive, negative, positive. Now for part 2, there are no inflection values because although the signs change at positive and negative 2, they aren't included in the domain. So then part 3 now, G is concave up like a cup from negative infinity to negative 2 and also from 2 to infinity. And G is concave down like a frown on the interval between negative 2 and 2. All right, so we'll do one more example. Sometimes you don't have to do all of this work if you know what the graph looks like. So this time we'll try letter F. X to the fourth looks like x squared, but just a little flatter. All right, so you can just look at this, and we don't really have to worry about checking the first and second derivative, but it's easy enough, so I'll do it. G double prime would be 12x squared. Oh, where does that equal 0? At x equals 0. And if you look at the graph, does G have any inflection value? So that's the possible ones. But in fact, there are no inflection values. And if you look at it, we don't even need a sign chart here, part 3. It's concave up like a cup, all the way from negative infinity to infinity. All right, so that'll do for today.